Good morning. Yes, thank you, Julia, and welcome here from beautiful Neillsville, Wisconsin. And I am working remotely today and enjoying some rain. It's unusual that we're calling or needing rain in May, but definitely something very much needed here in our area. So we'll take a beautiful rain day today. But we've got something also dealing with spring on the schedule, and that's maple syrup. And today I want to discuss with you some of the energy efficiency and energy aspects associated with maple syrup production. And in my title here, it's in the pan. And really that's what maple syrup production comes down to, boiling and getting rid of water from the pan. So we'll start from here. And thanks, Julie. If anything comes up, let me know. Otherwise, we'll be taking questions at the end of the presentation. Okay, maple syrup and maple syrup production usually starts from a hobby. And this is just a picture of our small operation here on my family farm. And I started the tradition of maple syrup production. My parents actually left the farm for a 3-day vacation, the first time I ever saw my parents leave the farm. And when they returned, I had about 20 trees tapped with small PVC pipes and ice cream buckets that I hung from the contraption that I had set up with the PVC pipes. So they came back, there was maple sap, and from there we decided to try and make some maple syrup. And one thing you'll note with maple syrup production is there's many different sizes and scales and many ways to do it, and it doesn't have to be very complicated. I know a lot of people that will get a few gallons and just boil off in their house. Others will set up a pan out in the middle of the yard and cook on a bonfire, very traditional to what the Native Americans used to do. So it goes from small to very large and complex commercial operations, which we'll cover in this report. But I think the big thing to walk away with here from the introduction is that many times maple syrup production starts as a hobby, and many of the big producers look at it more as a hobby as well. But as we'll see, there is a lot of energy input, and maple syrup production is very energy intensive. So what is energy's role in maple syrup production? Well, when you look at it, maple syrup is energy. It's a sugar, so from the very basic elemental component, maple syrup is energy. But also, maple syrup requires significant energy to produce it. And without energy, we wouldn't have maple syrup. Another thing to consider with maple syrup production is the seasonality. Maple syrup production, sap production occurs in the spring. It is fostered with the freeze-thaw conditions of spring, and the maple syrup season really is dictated by nature. So in most cases it's short. There's only a 2 to maybe 5 or 6 week window where conditions are perfect, optimal to make the maple sap run. It can be very short, a handful of days, a week or two in some cases, or there may not be hardly a season at all. There was one year where it lasted about 3 days in our area. And as you move south in the United States, the season may be more maybe shorter. It may be more susceptible to a short or infrequent seasons, depending on how the area and the landscape warms up. Another component of maple syrup production that really sways how things work out on the energy side is most operations work with a wood-based energy supply. And on the smaller hobby side, wood is usually a very readily available component. You collect sap in the woods. You've got woods in most cases that you have access to get a wood biomass, and wood is just a natural energy source for using for use in boiling and removing water for the maple syrup production. In many cases, this wood is looked upon as being free because it's so readily available in your woods around you. But there is a cost to that, whether you're buying it by this semi-load or you're producing it, cutting it, harvesting it, and splitting it. And then the last thing I covered earlier is there's a hobby nature to the business of maple syrup production. And as production increases, as the scale of the process increases, you really need to start to look at what is the business side of this venture, because when you're putting in a lot of energy, that energy also has a cost factor associated with it. And I think a lot of producers overlook the full cost side of production. So here's some production terms that if you're not really familiar with maple syrup production, that you may want to know. The first term I want to just discuss is this freeze-thaw cycle. And this is really what produces and gets the sap flowing in the maple trees. And maple trees are one of a number of different types of trees that are, or sugar-producing trees that are available. Other sugar-producing trees in the maple family include the basswood, or not basswood, sorry, box elder. The box elder. There are also sap trees. Yellow birch produces sap. Some of the nut trees, like the black walnut, butternut, they will also produce a sugar sap. So there's a number of different trees that will produce sap during this freeze-thaw cycle. And to get optimal sap flow, you need the nighttime to be below freezing, preferably in that mid to upper 20-degree range. And then during the day, that temperature increases to the mid-40s. This allows for essentially a change in pressure internally and externally on the tree. And this change in pressure, a high pressure on the inside of the tree, pushes that sap out, and that freeze-thaw action helps change the pressure grade inside and versus outside the tree. What happens if we do not get that freezing cycle is you lose that internal pressure in the tree, and it essentially stops flowing out the sap. The sap quits flowing. So that freeze-thaw cycle is critical, and we have ways to trick that now to some extent, but without freeze-thaw, you really cannot have a natural maple sap flow. And if you have 3 consecutive days without any freezing at night, that sap will stop flowing, and if it stays too warm too long and the trees begin to bud, then you lose that entire window of when that sap could possibly flow. The next term to discuss is the Rule of 86, and this goes back to early 1900s, and it was a common principle set up to determine the rough volume of sap based on the sugar content. So a scientist researched the sugar and found out that if you take 86 and divide that by the percent of sugar in the sap, then you can determine roughly how many gallons of sap there is. And this probably helped when people initially started to collect sap and buy sap and sell sap as a potential trading commodity. There are a number of places throughout sap producing areas that will accept sap and buy the sap from producers and then concentrate it and boil it down and either sell the maple syrup or return some of the maple syrup on a share basis. So this becomes a pretty common rule that you'll hear in the maple syrup realm. And this is a very basic example in what we usually consider as the base value for maple syrup and maple sap. Most maple sap is going to be, or the average sap is going to be about 2% sugar. So if we take that 86 divided by 2%, we get 42 gallons of sap. This plays into the next term here, which is Brix. And Brix is a measurement of the sugar content, or 1 gram of sucrose sugar in 100 grams of aqueous solution. And when we're looking at a finished maple syrup product, we're looking for that magic number of 66% Brix or 66% sugar. And sap can range from 1.8 to 2.8 Brix depending on the tree, depending on the year, depending on the time of year. So even that sap content varies quite a bit between years and even within the season. And how do we determine the Brix in maple syrup? Well, we've got a thermometer called a maple syrup hydrometer. This is very similar to candy hydrometers used for candy making. And it's an instrument used to measure the specific density of maple syrup. And I've got a picture of one here on the right. And this hydrometer is set up to factor the Brix at 66% sugar, and another component, the Baum, which is a final specific density of 35.6. And that is what most producers use to determine when to either remove this maple syrup from the pan or when they cook down the syrup to the final content. The scale of measure can vary, or varies, and there's two different lines to determine when the maple syrup is hot and when it is cold, because it has a different density based on temperature, and anybody might recognize that when they go to pour the syrup out. It's a lot thicker and stickier when it is cold versus when it's warmed. Now let's get to a little bit more of the energy side here. Maple syrup production is very energy intense. And in the table here, we lay out some of the low efficiency to high efficiency systems. And if using fuel oil, which a lot of the commercial systems use, a low efficiency system is going to require almost 5 gallons of fuel oil to produce 1 gallon of syrup. So when I said maple syrup equals energy, we really are pouring energy into producing a gallon of maple syrup. And even with a high efficiency straight pan system, we're going to need almost 3.5 gallons of fuel oil to produce 1 gallon of maple syrup. So when you buy a quart of maple syrup or a pint of maple syrup at a very high cost, maybe you can start to see why some of that cost is factored in there. And to put some numbers onto it, it takes about 400,000 to 500 BTUs to produce 1 gallon of maple syrup. Now, I threw in, or about 2 wheelbarrows of wood. Wood's really hard to put a number on because there are so many different variables in the quality of the wood, moisture content of the wood, and the type of wood. So while it's easy to get a solid number of how many gallons a person might use, getting a good value on the amount of wood being used is difficult, and that's one thing that you will run into if you're an energy auditor or looking at assisting producers in doing energy audits on maple syrup facilities and processes. Is wood biomass is a really hard component to calculate out with. Now, for every gallon of maple syrup, we noted earlier, there's roughly 42 gallons of water, and so this water needs to be removed to concentrate it and produce the final sugar and maple syrup content. And energy energy itself is the major component in the cost of production, and it accounts for 25% of the processing cost and almost 14% of the total cost. And I would venture to say it's even higher than that, for most hobby type systems where people are focused mostly on the cost input of the energy going into it. In 2003, Wisconsin survey found that these following energy sources for maple syrup production, 49% of systems were heated using oil, 45% utilized wood, and 3% utilized natural gas, and another 3% utilized propane. It was about an even split between natural gas and propane. So here in Wisconsin, maple syrup production is heavily intense on the oil side and wood side as well. The heating oil side probably breaks down to more of the commercial type operations, whereas the more of the traditional systems and hobby type operations consume more wood. So that just gives you an idea of what you're going to be running into with energy sources. When it comes to maple syrup production, the main component is the boiling down and concentrating in the pan. And so the magic is in the pan. And the best way, the quickest and most efficient way to process sap is to maximize the surface area of the pan. And you can see the top picture here shows a fluted pan where the pan actually has components that go up into the sap and down and up and down to create more surface area to allow that better heat transfer. And these new flue pan designs increase the surface area to a rate that they can actually increase evaporation by 50% and increase fuel efficiency by 20%. And they found that the optimal flue depth is between 7.5 and 11.5 inches deep. So these are pretty large pans to allow for the optimal conditions to maximize evaporation. The next efficiency measure that needs to be looked at on a system is an efficient arch or firebox. So the pan rests on an arch or a firebox, and that then is where you heat the system and provide that either the fuel oil heating system or a wood heating system. Now, a couple things to consider with a firebox design is it's best to completely insulate the firebox if possible. And it's recommended to use an 8-pound ceramic blanket. And this blanket is around a 2,600 degree F fire rating. So this material is made to handle a real high heat. It's also important to have an airtight system, especially if you're incorporating a forced draft or forced air system, and we'll talk a little bit more about that now, because air is a very crucial component in ensuring a proper burning system. So we need an adequate air supply, and in a lot of traditional systems where they just use a natural draft to pull air through the burning coals and exhaust it through the smokestack, that usually doesn't provide enough air to create a optimal burn. So a forced draft system ensures a adequate oxygen supply. And when you're looking at a system that's working, if the system has black smoke, that means there's incomplete combustion and more air is necessary. You need more oxygen. If the system has a clean white smoke or no smoke at all, then that system is likely working the way it was designed, and there's enough oxygen there to complete combustion. Forced air results in adequate oxygen, and it also supplies turbulence in a wood system. A lot of times these coals will just pile up, and you may have a foot of red hot coals, but because there isn't adequate oxygen there, you're really not getting the full heat value out of those coals, and they'll just add up, and that's something that's always happened and been a problem in our small system. We haven't had adequate air supply, and probably something I'll try to incorporate here in the future. But a little bit of air can go a long ways. And the big thing is a forced draft system can increase the BTU of output of the wood by 10 to 20%, and this reduces consumption by 30 to 50%. So it drastically reduces consumption, and there's two benefits to that. One, you don't have to make as much wood because you're not using as much wood, and two, you don't have to feed the system as much. And every time you open the system up, it cools the pan down. Every time you have to restart wood, it disrupts the burning process, and it reduces the heating efficiency of the overall system. Another option that energy efficiency option to consider in the boiling process is a preheat and heat recovery system. And a preheater can produce 13% fuel savings. And this is an example of a parallel flow preheater. It's a series of tubes that the sap flows through and it sits above the pan, so that steam that flows off of the pan goes up through these tubes, preheats the sap, and then exits a shroud or cover through a steam vent. Now, a key thing is there needs to be a drip pan underneath, because that drip pan will catch the condensate that condensates on these cold sap water preheating lines. So you're really not benefiting yourself with a preheater in this style of preheater if the condensate's dripping back into the pan. So those are some important components in a heat recovery unit. A steam enhanced unit will be shown next, but that has even greater fuel savings, about a 40% fuel savings, and that uses heat and captures heat in a little bit different way. But both options increase the rate of evaporation, and anytime you can increase the rate, you're saving time. Time allows for greater flow through, and allows you to put more sap through the process. And it reduces labor and increases capacity, which help you as a producer produce more product. So again, the preheater captures heat from the evaporator exhaust, allows it to preheat the sap. The cold sap is circulated through these copper tubes, and the steam condenses on the cooler pipe surface and transfers the heat to the sap. And again, this drip pan is necessary to collect the condensate. And this preheating system can increase sap efficiency 15 to 22%, or 15 to 20%. So it's a pretty good way to gain some efficiency, and they're pretty standard, simple season system to install. There's no parasitic loads essentially associated with it. It's just, in this case, a simple ball float system that allows more sap to enter into the pan as the pan gets cooked down. A steam-enhanced or steam-away system uses a little bit different arrangement to capture heat and optimize the preheating of the system. And this second system uses a secondary sap pan, a V-channeled fluted sap pan that condenses the steam and channels away the condensate. And in this system, an air blower is used to inject ambient dry air into that preheating sap to increase the turbulence and bubbling. And it's kind of mimicking the boiling process, but not quite at that boiling temperature. So you're bubbling air through that sap and taking a low humidity air and allowing it to leave the sap at 100% humidity. So a steam-enhanced preheating system results in a much more concentrated sap. We can double our sugar concentration in that sap before going into the pan. So we can take it from 2% sugar to almost 4% sugar before you even start to boil it off. And it also preheats then the sap to an increase to almost 190 to 200 degrees Fahrenheit. So the steam-enhanced unit really takes that preheating to the next level, but there is an external parasitic load there with the air blower. You need to have a much better condensate system, and so it requires a little bit more technology to install. The final system, and probably the system that's getting the most attention these days, is a reverse osmosis system. And essentially, you're pulling the water out of the sap. And a reverse osmosis system can remove up to 75% of the water and reduce energy costs by 50 to 75%. So how do we reduce costs? We avoid boiling water altogether. And so this system allows for an increased expansion, increased production by shortening the time necessary to boil and the energy needed to produce a given output of syrup. So this is really a good system to avoid costs and avoid the time and labor going into the boiling, the most time critical step. And reverse osmosis systems are available in a wide range of sizes. So they can work from the very small, like a 50 gallon per hour system, to handle a commercial size operation of up to 4,000 gallons of sap processed per hour. And it allows, this technology is applicable through all applications. And how does reverse osmosis work? Well, sap is pressurized through a semi-permeable membrane, and the water weeps through the permeable membrane, while the sugar, which is a slightly smaller molecule or larger molecule, does not pass through the membrane, and evaporates out through the bottom of the system. Now, these systems are designed to run multiple runs. So usually you remove about 50 to 65% of the water in the first run, and then you'll run the concentrated sap through a second time, and that second run of concentrate is then ready for the pan. And we can increase the sugar content up to 8%. So we've taken a 2% product, increased it to 8%, and removed a lot of the water from the system. This system requires a mechanical pumping system to produce pressure. So there is a substantial electric load associated with a reverse osmosis system. And so a facility will need to have access to electricity, and there is a cost of electrical consumption that needs to be factored in there. And these systems can use between 300 and 600 kilowatt hours to process 600 gallons per hour of sap. And in the end, that can result in an electric cost of $30 to $50 compared to an $80 fuel oil cost. So there are savings there. There are cost savings. It isn't a free lunch. So that needs to be factored in there. I have here time savings. There is a huge time savings. And so a lot of producers are going to reverse osmosis just as much on the merit of the amount of time that is saved from boiling and the increased flow through that they can have through the system. What effect does reverse osmosis have on fuel oil consumption? In the graph here, we've split out, again, a lower efficiency evaporation process to a higher efficiency evaporation process. And that low efficiency system that almost used 5 gallons of fuel oil can be reduced to under 2 gallons of fuel oil with the aid of a reverse osmosis system. And a high efficiency evaporator may require only 1.2 gallons of fuel oil to process that gallon of maple syrup. So we're almost down to a 1-to-1 oil to maple syrup ratio. Another point here to consider, and this is not an energy efficiency component, but this is something we're seeing more and more in the woods and is becoming a major component in maple syrup production, and that is a vacuum line system. A number of producers have moved to a tubing system where tubes are laid out throughout the woods that go to the maple sap trees, and these lines then flow the sap to a central gathering station and allow it to be collected and transferred from that central station, or it may go directly to the cookhouse, depending on how it's laid out. So these tube lines have made it a lot easier to collect sap. But what they've found that is if they put on a vacuum system or a vacuum pressure through that tube line, they can actually increase the flow of maple sap. And one of the big benefits are if you don't get the optimal conditions, that freeze-thaw process at night, you can still withdraw or mimic that high pressure in the tree by putting on a lower pressure through the vacuum and creating that pressure differential artificially with this vacuum system. And this again mimics that natural pressure cycle, allowing the sap to flow. And
Joe?
Yes.
I've got a comment from Autumn Carilla. She is actually one of our New Hampshire office people that does maple syrup as well for the audience. Is the consumption essentially 0.5 to 1 kWh per gallon of finished product?
That just depends. That's I believe so. I think that's gallon per hour of finished product. Well, you know what? I don't know for sure.
In reference to the reverse osmosis machine.
Yeah. I can't say for sure. I'd have to look back where I pulled that number. So yeah, I'm sorry, Autumn. I can follow up with you and let you know on that. I can't remember where I pulled that. I believe I pulled that out of the Massachusetts guidebook we put together, but I'm not sure on that statistic. Sorry. So we'll go back to the vacuum line system. A new area of advancement in maple syrup production is this vacuum line system, and I think we're going to see a lot more of this in implementation, and something to be aware of. The system's quite simple. It utilizes a 5 horsepower to 10 horsepower vacuum system. 1 CFM per 100 taps is the kind of the standard design metric, and 1 CFM per horsepower. The system itself is designed to produce about 20 inches of vacuum at the vacuum pump. So in the end, these are pretty small systems, pretty standardized systems. It's comparable to a vacuum system used for milk pipelines. So something that could be installed very easily by dairy specialists and dairy installers out there. The system, however, is set up to be operated when temperatures are above freezing. So temperatures still need to be above freezing. But again, the vacuum process will draw sap out of the trees, even if you don't get that natural freeze-thaw action at night. There is a natural vacuum system that aids in increased flow from the trees. It will not work if you don't get that freeze-thaw cycle, but it does increase flow when you do get that natural cycle, and that can be produced by maintaining a 5% or greater slope in the line, and essentially using that pressure head to help draw the sap out. Like everything, again, there's no free lunch here, and there is a net increase in electricity. And so this is not an energy efficiency measure. And there is a positive production efficiency here. So that's the big reason producers are going to be moving to this technology, is they can really increase production, increase yield from the sap, and per tree sap production. We will likely see more of this going in, especially on commercial systems that want to see more consistency throughout their maple syrup season. Other consumers in the sugar shack include UV radiation for sterilizing sap. It utilizes UV lights, and that ultraviolet radiation kills any bacteria or microbials that might happen to get in the sap. And there is a very limited parasitic load associated with it. So there is some energy use that will be required through that system. Another common energy system is a candy making and specialty processing devices, and you'll find these in a lot of operations. And there may be heaters on candy molds. There's pumps and heaters associated with filtration systems and the filtering systems to clean and process the final product, as well as heating for canning systems, the heating of the sap and heating of the jars and canning. So throughout the entire sap production cycle, there's a lot of energy for heating and the components. And these systems often use electric heating elements and warming irons. So these, in most cases, have very similar loads to household cooking items and household cooking components. And another major energy and parasitic load to factor in on maple syrup production are pumps, and more pumps. As we increase the flow of the systems, increase the throughput of the systems, we need sap pumps to move sap from area to area. We need condensate pumps to pump the water condensate from the preheaters or steam away systems, and pumps to pump the maple syrup as we produce more and more gallons per hour of maple syrup. Kind of close things out here, but I'll give you a couple examples of projects we've worked with. And a traditional wood furnace system here processes about 8,000 gallons of sap per year, or 250 gallons of syrup in the operation. Under our analysis, we found that a steam away system could be incorporated into the flat pan system, and that would have about a $380 savings, but a project cost of almost $6,500. And that was primarily high cost was primarily a result of needs to upgrade the pan system, upgrade the system itself to accept that steam away system. And so in the end, that project had a 17.3-year payback, and would save about 7.5 cords of wood, or almost 50% of the woods consumed in that project. So we have a high savings, but wood in this case was supplied by hunters, and a little bit was purchased if necessary, but wood was a cheap energy source. Now, we also looked at the potential for an air-injected arch evaporator to help them improve the efficiency of the burning process, and that had a more favorable payback, and the project cost would be a bit lower. So in this case, it was just short of a 7-year payback, and you still saved about the same amount of wood. So the farm ended up moving ahead with that update project and improve the burning process. But again, you can see in this case, while they're producing 250 gallons, the economies of scale just don't allow for some of these more in-depth processes. And reverse osmosis was also analyzed, but this system was a remote system, did not have electricity. So other factors need to be factored in as well when electricity may not be available at the site. And in this case, reverse osmosis isn't going to be beneficial or cost feasible from an energy cost saving standpoint. So again, when working with a wood-based energy supply, there's a limited payback if wood is cheap and highly available. The next example here, we're looking at a commercial oil-fueled system, and this is a larger system here, processing 50,000 gallons of sap per year, or 2,000 gallons of syrup. And in this case, we recommended a steam away system. They had the fluted pan and an air-forced arch, and had all of the technology on the pan side, and as well as a reverse osmosis system. But we found that a steam away system would have a lot of good benefits as well. So that steam away system was projected to save over 600 gallons of fuel oil a year, almost 50% savings, and have a 2-year payback. So you can really see the economy of scale helping in this situation, where the increased time of use and flow-through benefit the financial payback of a system. Plus, the system was already upgraded, and it made the retrofit component much easier, which reduced the project cost. So in this case, a steam-away system was a very good and easy decision to improve their process. So that'll bring me to conclusion here. And hobby or business, maple syrup production has a significant energy cost and really needs to be looked at seriously. There are currently many energy efficiency opportunities, but in a lot of cases, these opportunities are limited by the variability in production, from year to year and season to season, as well as the overall time of use, the fact that there is such a short season. So when looking at energy efficiency opportunities, you really need to factor in these costs with the time of use and determine what are your end benefits, what are your end needs and desires. And lastly here, energy efficiency, increased production, and a reduction in labor go hand in hand in many cases. So it's, in a lot of cases, energy efficiency is a win-win on many levels. And that's why it makes energy efficiency on maple syrup production systems a fun group of projects to work with, and why producers are so interested in improving efficiency. So at that point, we'll take questions, and also I'll address Autumn's question here. And Autumn, the factor figured out there was, I believe, on a SAP basis. So, are there any other questions?
I was just going to say, Joe, that if you don't already have the chat box on the right-hand side of your screen, go to the top part of your upper right-hand corner of your screen. There should be a little chat bubble. If it's blue, then you should see it. If it's gray, go ahead and click it so it does turn blue, and the chat box will appear on the right-hand side of your screen. And go ahead and type in your questions. Like I said before at the beginning of the presentation, Joe did a previous presentation on irrigation. He will be also presenting in July on biogas. So we'll just take a few minutes here and wait for some of the questions to come in. All right, we do have a question here. On the slide showing the electric cost savings, it has $30 to $50 savings. Is this a per hour cost or total cost?
That's a, let's go back to that. That's a, in reference to that 300 to 600 kilowatt hours. So that would be probably the entire process cost.
All right, we've got another one. How do you deal with GHG emissions from wood emission savings?
Ooh, how do you handle greenhouse gas emissions? Well, I mean, that's a big question out there in terms of how do you factor in renewable biomasses versus non-renewable. So I'll let the environmentalists and those debating that debate that. I guess in most cases you've got a limited system there. I would say if you had to start putting on bagging plants and some of these other greenhouse gas and emission related processes into a wood system, you're likely going to no longer be using wood. So then you ask yourself, are you better off using wood from the forest you're working with, or changing that to fuel oil or propane or natural gas, a non-renewable resource. So I guess I don't have any real good answers to that, but I would say from just a process standpoint, it would pretty much deem maple syrup production with wood very difficult.
All right, I've got another question here. Does the reverse osmosis taste different than the boil-off method?
It does not. It tastes the same because you're still concentrating and going through that process just like you would if you weren't removing some of that water from the boiling process.
I've got a follow-up question to the greenhouse gas question. A better question would be, if using reverse osmosis, how do you account for greenhouse gas savings in ag E&P?
Oh, how do we do that? Well, we would look at the amount of energy savings or fuel savings and factor that in. So if we were to put in reverse osmosis, we could reduce, the oil or wood fuel consumption, and so we factor it in by the reduced wood consumption or fuel consumption. And I guess the bigger thing is there are some tools like Comet that are used to determine greenhouse gas savings. We've utilized a group of greenhouse gas calculations based from the work we've done with the University of Wisconsin Extension and Scott Sanford, as well as general research literature components for greenhouse gas consumption from wood burning. So those are the values we use in determining greenhouse gas related emissions.
All right, we've got another question. Does the reverse osmosis process need to be followed by additional boiling off? Your example in farm number 2 using oil and reverse osmosis.
Yes. Oh, yeah. The reverse osmosis will only concentrate the sap to about 8% sugar. So we need to still take that from 8% sugar to 66% sugar for the final product. You'd have to, I don't even know if it probably theoretically is possible, but you could not run a sap through a membrane enough to get it to the extent of maple syrup. So it's always going to require some sort of boiling or some other way of removing water.
I don't see anything else. We'll give you a few more minutes if you have any more questions. Joe, if you could put up your contact information again. We have lots of people that can answer your questions about maple syrup or any other agricultural services. We have our services department here in Wisconsin. We have agricultural people out in New Hampshire. As you can see, Autumn Carilla is out there as well. So again, if you have any questions on the maple syrup or anything like that, go ahead and give us a call, or you can email me specifically about the webinar. Again, this is recorded, so feel free to give me a shout out on your email. And thank you for joining us today.